Am I on? Yeah, okay. Let us begin. Okay, so hello, I'm David. I'm one of the organisers of this wonderful meetup. And today I'm going to give a talk about Django and the database, and particularly two key concepts that, to be honest, I've only really started to think about quite recently. And in my experience, Django developers don't think about this stuff as much maybe as we should. So I'm going to look at two main concepts. The first concept is atomicity. Don't worry if you don't know what that means yet. And the second one is concurrency. And finally, I'm going to look at some caveats or warnings associated with working with these things, because you can get some nasty issues if you're not careful. It's going to be a sort of fairly longish talk, about half an hour, so pace yourselves. But hopefully you'll be amazingly entertained and the time will pass very quickly. So, I'm going to talk about an imaginary bank that I built with some bad code, Shamtamdare. It went through many different phases and different bugs, and basically the bugs happened because I didn't properly engage with the concepts of atomicity and concurrency. So what we're going to do is we're going to look at some code and in kind of some detail look at what the problems are with it, and I'm going to try and encourage you to sort of start thinking about these concepts if you don't already. So this is the code of Shamtamdare version 1. There's not very much of it, and we're going to keep on going back to this. So I'm just going to spend a little bit of time talking about it, just so we're all clear on how the basics work. So actually, could I just get a show of hands? Who here actually knows how to program in Django? I'm hoping it's everyone pretty much. Who does? Okay, so here we have two models. We have an account model, and all the account model is it's just like a bank account in Shamtamdare. Doesn't have any other extra information. We've also got a ledger entry model. And what the ledger entry is you can think of it like a line on your bank statement or something. So it would be something either coming in or going out. That's all you really need to know about that one. And finally, we have our transfer function. And what the transfer function does is it takes a source account and a destination account and an amount, and it checks to see if the source account has enough money in the account. And if it does, it creates two ledger entries. The one is a minus version of the amount, which is coming out of the source account. And the second one is a plus version of the amount, which is going into the destination account. So hopefully this is fairly simple and seems hopefully fairly unproblematic. It's kind of double entry accounting. However, we launched Shamtamdare version 1 and everything seemed to be working fine for a while. But then we sort of started building extra things on the system and it started getting a bit more complicated. And suddenly I realized that this was happening. Not this is concept 1 that I'm about to tell you about. This was happening. The book balance was suddenly going down. What I mean by the book balance is if you kind of add up all the debits and credits, you'd expect that to come to 0. But it wasn't balancing. For some reason, we were losing money out of our database records, which is obviously a very bad thing, because if you're a bank and your database has got corrupted over where your money is, then, well, you'd be a sham. So I tried to hunt down why this might be happening. And I was looking at this code. So I was looking at the transfer code, and it creates two ledger entries. And I just suddenly thought, well, the first ledger entry is a negative amount. The second one is a positive amount. What happens if there's some problem with this second ledger entry? Maybe the first entry is getting written, but the second one isn't. And that would explain why we would have this issue. So this brings us to the concept of atomicity, which is the state or fact of being composed of indivisible units. So what I realized is when you want to make a transfer in a database system, you don't want to do it half. It would be better not to do it at all. Hopefully that's pretty obvious to everyone. But if there's some kind of failure, I wouldn't want to like just do it a bit because it would corrupt the database. So what I realized is I wanted to find a way of making this transfer atomic, indivisible. Both queries that it submits, I wanted either both of them to happen or neither. Now, this is a little sidetrack, which is to talk about database transactions. And this is the way databases handle this idea. So when we make queries to a database, we can make lots of different queries, but it's also possible to wrap them in what's called a transaction. Show of hands, who here is familiar with database transactions? Okay, so about 2/3, that's good. So transactions are a way of wrapping queries up into discrete blocks. And what you can do with a transaction is, if there's a failure, then that transaction never makes its way into the database. It kind of gets committed all at once. So when I talk about a transaction being committed, what I'm talking about is all the queries get added to the database in one go. So this is a little quiz about Django. So this is our code. We've got the transfer code, which you've already seen, and we've also got a view, which is like an API endpoint, which receives the source, destination, and the amount. And what it does is it just transfers it. It doesn't really matter about the details. So my question is, if this second ledger entry fails for some reason and raises an exception, will the first ledger entry be written to the database? Yes, no, or it depends. So gather your thoughts, and then I'm going to ask for a show of hands. You can abstain. So who thinks it is A? Yes. 1, 2. Okay, 3. Yeah. Who thinks it's no? No one. And who thinks it depends? Okay, so there's lots of abstentions, but the good news is it depends. You won. So can anyone tell me on what? What does it depend on? Yes.
On Django settings.
Great, yes, and what particularly?
To wrap or not views on atomic requests.
You won the prize. So there's a very simple way of making sure that your views get wrapped in transactions. It's this setting. By default, it's turned off. But if you turn it on, then every view that you get, if there's any unhandled exception, then nothing that you do to the database will get committed. So this is really great, particularly if you're doing financial stuff, because you can look and you go, oh no, there was some bug in my logs. And you can look at it and you go, it's all right. It won't have messed up the database because that will not have been committed. And then you can fix the bug, and then hopefully it will start working again. So atomic requests is really great if you're wanting to keep the database from being corrupted by certain complex requests. So version 2, all I did was I turned atomic requests on, and suddenly the book balance worked. So I was very pleased, and so were my superiors. So, however, we decided to scale Shamtamdare a bit because we were getting lots more users, and we decided to put the transfer function in the celery task. Who here is, do I need to explain celery? Could you put your hand up if you're clear about what celery is? Okay, pretty much everyone. Okay, really quickly for those who don't. It's just a way of, it's a process that runs outside the request response cycle, and you can just hand it off to that, and then it will run like a long-running task. So it's very useful for longer-running tasks that you don't want your request to wait for to complete. Okay, so we moved it into a celery, and oh no, it broke again. Can anyone tell me why? Exactly. So celery tasks are not a request. So, um, so it won't be wrapped in atomic requests. It's a really big gotcha. You can think, oh, fine, I'm all good. And then as soon as you move into celery tasks, you lose that atomicity. So there's a very simple way to do this, which is called transaction.atomic. It's a context decorator, and literally you just do with transaction atomic, and then you can put all sorts of stuff within that. And then if an exception is raised and it's not handled, then just like with atomic requests, it will be rolled back. It's you can put this anywhere and you can nest it as well. So it's really like a bit of a no-brainer. Like if you've got something that you want to be atomic, wrap it in that. So version 4, I wrap my transfer in transaction atomic, and the book's balance. Brilliant. Okay, so that is part 1 over. Does anyone have any questions so far about atomicity? Cool. Okay, I'm going to move on. So concept number 2 is concurrency. This is a little bit more complicated. So Santander scales again. We've got loads of users, and they're all making requests at once. But the problem is we've suddenly got this problem where some users have negative account balances, and that seems impossible. If you look at the code, we check to see if there's enough money before making the transfer. So why is it a problem? And so I looked at the code, and I suddenly realized, oh, if there are 2 celery workers working at once, or this could be requests as well, like Django often has multiple processes handling things. So if there's 2 processes that are handling at once, let's say worker 1 wants to transfer £100 and worker 2 wants to transfer £50, both of them check the balance first. Yeah, great, £100. And this one checks £50, and then £100 reduces the balance, and then £50 reduces the balance, and suddenly we've gone into an overdraft when we didn't want it. So that's obviously not a good thing. And what I'm going to talk about for the rest of this concurrency bit is basically how do you avoid that happening? And the answer is that you don't let them run concurrently, basically. But how do you do that? So let's have a little bit of a look at how databases handle concurrency. If you did a computer science degree, this will probably all be very obvious, and I apologize. But it's not necessarily obvious to everyone. So databases allow lots of processes at once to modify their data. So it's not just like get in the queue, ask the database to do some things, and then like the next person comes along, because otherwise that would take ages. So there's all sorts of processes, all sorts of transactions, adjusting things. And in order to do this, it needs to kind of make some decisions, some difficult decisions about how to allow that. So I'm going to go through and look first at reading and then at writing and get our head around the details of when it makes these decisions. So with reading, I want to imagine that we've got a table here, and it starts off with a value of 0. And transaction 1 starts, then transaction 2 starts, and then transaction 1 sets the value to 1. But before it commits down here, transaction 2 selects the value. In other words, it reads it. Now, my question is, and I should say this is Postgres. I'm kind of focusing a bit on Postgres for this talk. What happens? Is it A, transaction 2 will read the value of 0? Is it B, transaction 2 will read the value of 1 straight away? Is it C, transaction 2 will read the value of 1, but it will wait until transaction 1 completes, and then it will get the value of 1? Or is it D, it depends? So could we get a show of hands for these different things? So who thinks that it reads the value of 0, A?
Postgres with defaults?
Well, possibly you might vote for D. So who thinks A? And by the way, Alan's definitely wrong. Who thinks B? Okay, who thinks C? Okay, and who thinks D? Okay, Alan gave it away a bit. It is D. It does depend. So on what is the question? Take it away, Anand.
Depends on the isolation
Exactly. So database isolation levels. I have to admit, I did not know about these until quite recently. And they're quite interesting. So basically, there is no one right way to handle concurrent reads and concurrent writes. You can have different strategies, and you can set it as a default on the database, and you can also set it in the transaction, I think. I'm not sure, but I think so. Now, there are 4 different levels. Serializable is like really kind of strict, and it basically like gives you errors if you ever try and do anything concurrently, and it's quite difficult to handle that kind of thing. So that's kind of quite an extreme approach. At the other extreme is read uncommitted, which is very permissive and fast, but it doesn't. It's a bit unsafe. I have a feeling, I'm not sure if someone could correct me, but maybe no SQL databases use things like that. I'm not sure yeah. But that's maybe one of the reasons why they're quite fast, is because there's less checking. Anyway, the middle ones, repeatable read and read committed, which are quite similar, are sort of a mixed approach. And MySQL defaults to repeatable read, and Postgres defaults to read committed. Now, I'm only going to talk about read committed because it's the default. Sorry, I'm about to sneeze. Obviously, I'm not. But I think probably most of what I say will apply if you're using MySQL. It's just subtly a little bit different, but it shouldn't matter too much. So this is the principle of how read committed handles reading. So basically, if you have a transaction and it writes a value, then no other transaction can see that value, can see that write, until the transaction is committed. This means if you open 2 Django sessions at once and start doing things to the database within the transaction before committing it, you will actually see different things in the 2 sessions. So you can think of it like the transaction kind of keeps its own local copy of data that's changed. And you'll see this denotes it being committed. So once we have the solid line, then that's finally when it becomes committed. So with this newfound knowledge, we're in read committed mode. What happens? So is it transaction 2 reads value 0 straight away? Is it transaction 2 reads value 1 straight away? Is it transaction 2 reads value 1 once transaction 1 commits? We know what it depends on. So could I have a show of hands? Who thinks it's A? Okay, yeah, 4, all right. Who thinks it's B? Nobody. Who thinks it's C? Quite a few, yeah. Okay, well, like what's interesting is actually, like none of us are really that sure, which is telling, isn't it? I mean, I wasn't sure, and I had to learn for this talk. So, so the answer is, I'm just going to go back to that. Records from other sessions will become visible as they are committed, not as they're written. So actually, it's the first one. Transaction 1 will set it to 1, but transaction 2 will see it as 0, which obviously is quite important to realize that's how databases work. And we'll see some of the gotchas about that in caveats at the end. So that's reading. Yes, that's the answer. Writing. So how does it handle concurrent writing? So let's imagine now we have transaction 1 and transaction 2, and they're both trying to set the value to their own number. So transaction 1 comes in first, sets the value to 1, but it hasn't committed yet. And then transaction 2 goes in, and it tries to commit it. And then transaction 1 does some other stuff. Transaction 2 tries to commit first, then transaction 1 afterwards. So my question is, what happens? These are the only 4 I could think of. So number 1, transaction 1 sets value to 1, and then transaction 2 overwrites value as 2. So it ends up as 2. And this all happens straight away. Or transaction 1 commits value 2, because it commits first, and then, because transaction 1 commits second, that commits value 1. Thirdly, transaction 2 waits until transaction 1 commits, and then it sets the value to 2, so it ends up as 2. Or, D, transaction 2 errors when it attempts to set value to the 2. So, and I'm going to add a fifth one, which is I don't know, because I think that's probably a good choice as well. So, who thinks A? Who thinks B? 2, 3. Who thinks C? Okay, a bit more. Who thinks D? And who thinks E? I don't know. Good honesty. Okay, so the answer is, actually I'm going to tell you about read committed writing before, and then you get a second chance armed with more knowledge. So the way read committed works with writing is records that sessions are writing to are marked as dirty immediately, and then other writers will wait until the lock is released. So what this means is you can think of it like there's an extra column for each record, and that's like a read-only kind of flag on it. And when a transaction sets a value, although it doesn't set the value to anything, it doesn't change the value. So as far as readers are concerned, they can still put it in. It does actually change it. It marks it as read-only or dirty or locked or whatever you want to call it. So it kind of sets a flag on the record to say, I've changed this. I haven't committed yet, but I've changed it, so don't change it. And then it stores its value, as we already know, kind of within its transaction. And then when it commits, that's when the value changes and the read-only flag is released. So I like to think of a metaphor of this as a bit like, imagine if you've got a kind of big filing cabinet full of papers that loads of people are constantly rummaging around in. Like everyone can always read the filing cabinet, but if you're like doing a bit of work, you can go in and get a piece of paper out and look at it. But if you want to change it, you kind of put a sticker on it, something saying like, I'm in the middle of working with this. So you put it back in the filing cabinet, but other people can look at it, but you like do your calculations, whatever, and then you go in, change it, and take the sticker off. And what happens is if someone else, according to this metaphor, wants to change that, then they'll come in and go, oh, there's a sticker on it. So they'll just sit there and like do nothing. They'll just literally sit there, and then eventually you'll come back and go, all right, here it is, and you're like, okay, thanks, and then you'll carry on. There is a setting where you can say, oh, forget it. But by default, it will sit there and wait. So, with this in mind, what happens? This is the same question as before. So, does transaction 1 set value to 1 and then T2 overwrites it? Does transaction 2 commit it first and then transaction 1 commits it? Does transaction 2 wait until T1 commits it and then overwrites it? Or is there an error? Do we know? Who thinks A? Who thinks B? Who thinks C? Yes, you are listening. Okay. So that's the right answer. So this is a sort of depiction of it. You see, when you're trying to set something that's already been marked as dirty, then that actually could be quite a long-running process. So you need to think about that when you're setting things in a transaction. Like your code might sit there for a few seconds even. So, armed with this knowledge, how do we prevent concurrency? This is what it's all about at the end of the day. So there is a final thing which I haven't talked about at the database level, and that's called select for update. And this is one simple way in which you can prevent concurrency. It's not the only way. But what select for update does is it's like a select, it's a read, but it behaves like a write. So if it reads, then it will mark it as read-only. It will acquire a lock. So we can see the flow here. Transaction 1 does a select for update at the beginning. Transaction 2 also does a select for update at the beginning. That's a way of saying, I don't want to do anything until I've got, like, I'm the only one that's doing it. So transaction 1 is the only one that's doing it. So it reads it, gets the value of 0, and then it marks it as read-only. Then transaction 2 tries to do the same, but it waits, doesn't do anything, it just sits there. Then transaction 1 does its thing, it sets the value, no change yet, and then it commits it. Great. As soon as that's committed, transaction 2's got the lock. So it then gets the value, and this time it gets the value of 1, which is what it wants really. Before, you remember, it will have got this value because it wasn't waiting until it had exclusive rights on that record. So then it gets it, and then it sets the value as 2, and everything is happy. So the way I think of select for update is it's a way of making a read query behave like a write query. We're coming into the home stretch about how to implement this in our Shamtam-Dare account system. So it's very simple actually. You just do this. So it's on the model manager. You just do select for update, and then you can use like get, or you can use filter or something like that. So it just kind of adds it to your query set. And the only other thing to know is that it must be called within a transaction. So you can't just use this willy-nilly. You need to make sure atomic request is on, or if it's in a celery task or something, that it's wrapped in a database transaction. But that can be at any point. You know, you could just wrap it, and then like within some nested functions, you could call select for update. Otherwise, it will raise that exception. So let's come back and look. How can we prevent concurrent transfers on the same source account? So all we want to do here is we just want to make sure we don't mind concurrent transfers as long as they're not happening from that source account, because then we get that problem. So I don't know if it's obvious to anyone, but does anyone have any suggestions about how we could do that in a simple way? I will give you a clue. It uses select for update.
To modify the source and destination variables.
So
The get there is a object.select for update.
yeah, okay. So Anand's suggesting that we do account.objects.select for update get.
Move the topic commits up, and then that would be
Perfect. Okay, that is the right answer. So if we think about this, I mean, to be honest, it's quite a heavy-handed way. I'm using it sort of as like an example, but because obviously it will lock the account for any other things as well. But if this transfer always, when it runs, it always does a select for update, then if another version of this transfer, which also does a select for update, runs, then it will wait. It's not going to stop stuff that doesn't use select for update from processing, but because we specifically want to make sure that transfer doesn't operate concurrently with another transfer, we can just lock it on the account object. So this is it. And this is called, I think it's called pessimistic locking. There are other ways of doing it, such as optimistic locking. But this is a kind of really simple way to do it. It does mean that things wait around a bit, but it's a small price to pay for no concurrency. So does anyone have any questions about this? Well, possibly that might be, I think that might be my next slide, actually. What's the bug?
well, I can overwrite the destination amount. So two different source accounts do a transfer in. One does me £20, and the second one that does me 10. My amount will only have gone up by 10.
So these aren't overwriting. These are entries, so they don't change. And so the way you work out the balance is by summing them up. So I think it's safe from that. Yeah, I don't think there's a particular bug in this, but there's one coming up. So Shamtam-Dare version 5, which is the final version, it works. The account balances are restored to normal, and all we needed to do is just put a select for update in. So simple. So caveats.
Shouldn't you have
Yes.
also selected for update on the destination?
That's a good question. Let's come back to that at the end. It's a really good question. 4 caveats. So caveat number one. Like, I have been stung by all of these, and they're horrible. So the first one is a task within a transaction. So let's imagine that we want to send a notification email, and we've got a Celery task here. So we create the ledger entry, and then we send the Celery notification email. Can anyone tell me what the problem is with this? In fact, there are two problems. It's not immediately obvious. Jerry knows because we did it together. Everyone's talking at once. Who's? Great. That is the first reason. So the email may get sent even if the transfer fails. So you really don't want to send stuff to Celery until you're sure it's happened. There's actually an even nastier bug. Let's say this wasn't an email, but like just something else that needed to get that model. Can anyone see what the bug is? No, it's not that.
Well, in this, the email the transaction may succeed, but then the email won't get sent.
Okay, I'm going to give you a clue. Let's imagine that like this takes quite a long time. Yes? No? Can't. No? Okay, I'm going to tell you. I mean, it's interesting that none of us know. This isn't in the database yet. When Celery gets it, it's not in the database. It's not committed. So Celery will just say, no, nothing with that ID. I really did not know that Celery did that, but it does. And you can verify it by opening two shells and then like create an object in one and then try and read it in the other, and it's not there until the transaction's committed. This isn't a problem when you're in auto commit mode, which you are by default. But once you move on to this, you need to be thinking about these things. So that's the second reason, is the email may not be able to get the entries from the database yet. It's a bit of a nasty bug because it's a race condition, because sometimes you run your tests or whatever and it seems to work fine because it doesn't take very long, but like you can suddenly get all these models not found because suddenly this is losing the race. So that's caveat one, big caveat. How to solve it? It's really easy. You use transaction on commit. This is all you do, and it just completely solves the problem. So whenever you're calling some kind of task, asynchronous task, you use transaction on commit, and you pass it a lambda of the Celery task, or you can pass it a callable. You just have to do that. I mean, it should be automatic, but you have to do it. Yes? Yes, that's great news. Okay, so if people didn't hear that, Celery 4 does this by default, because really there's never a case where you don't want to do this that I can think of. Yeah, oh, that's great. Yeah. Okay, caveat 2, spot the bug. So I changed this a bit, and I decided that I didn't want to do a select for update on. I didn't want to do a concurrency on destinations as well as sources. So I did this, so a select for update, and I did a filter instead. So it waits and it acquires the lock on both instead of just one. What's the bug? This killed me. It's so obvious once you see it.
Because it works in the shell.
Yeah, it does work in the shell.
Does it always acquire the two logs in the same order?
No.
That's how it does work.
I'll give you a clue. It doesn't acquire any locks. It doesn't work. Okay, so does the word lazy query sets mean anything to anyone? This never hits the database because filter is lazy, unlike get. So if you're using select for update as a kind of write action and you're using filter, you have to remember that query sets are lazy. And it's a really easy thing to miss, and then you'll only find out in production, potentially. So a simple way to do this is just wrap it in a Boolean, and then it will get evaluated. So that's caveat 2. Caveat 3, deadlocks. These are very scary until you understand what they are. The first time I saw my first deadlock, I was like, there's no way I'll ever be able to fix this. But if you see this error, it means that there's a deadlock between acquiring different locks. So this is how it happens. Let's say we've got process 1 that's trying to do select for update on 1 and 2. Well, process 2 is trying to do a select for update on 2 and 1. So you can imagine the first one, select for update isn't instant. So it acquires each row in turn. So if the first one acquires row 1 and the second one requires row 2, then they're going to wait for each other before they can do anything. And so it's a deadlock. Fortunately, Postgres is clever enough to work this out, and it will just give up. But so how do we fix it? Any ideas? Yes. No. I mean that isn't actually such a bad idea. Yeah. So yes. Any other ideas? Yes. Correct. So I just put in an order by ID. If you acquire them in the same order, then it won't cause the same problems. So I mean, there are probably more complex situations than this, but like essentially, you just need to think when you're acquiring locks as to the order in which you do them in. So in this case, this gets number 1, then this one tries to get number 1 and waits. Simple. The final caveat, and then we're at an end. So this is testing. This is a really annoying thing about select for update. So the problem with Django test case is it wraps everything in transaction. And that means if you're testing transactions, then it's not necessarily going to behave the same as your real production code. So an example might be that you might have a celery task that has a select for update that has been left out of an atomic block, and that will run fine in your test, but not in production. So you'll only find out about it when you don't want to. It's really annoying. There is a workaround, which is to use the confusingly named transaction test case, which doesn't wrap in a transaction. But you can think of transaction test cases as useful if you're having to think about transactions. So what transaction test case does is it's pretty much the same, but it does a full database truncate or something. So that's why you don't want to do that all the time, because it would be slower test-wise. And also you need to do that if you want to do things like rollbacks and any other stuff to do with the actual transactional things. I didn't tell you about rollbacks, but you can look in the Django docs. Okay, so in summary, thank you for bearing with me on this very long and detailed talk. Atomicity, atomic requests makes your request atomic, obviously. You can use transaction atomic to enforce atomicity when it's not in requests, and you can use you must use transaction on commit for tasks. With concurrency, just ask yourself, does your code handle concurrency? Is it going to be okay? Is it a possibility? Because you won't have tested for it probably. And if not, prevent it. A simple way, pessimistic locking using select for update. If it makes everything too slow, Google and learn better ways to do it. And 3 caveats. Query sets are lazy, so make sure your select for update is actually being evaluated. Number 2, avoid deadlocks by acquiring locks in a consistent order. And 3, test case wraps your code in a transaction. Be aware of it. Okay, so does anyone have any questions or comments? I know we had one about the source and destination accounts. So I'll rephrase the question, correct me if I'm wrong. So you were saying, why don't we acquire the lock on the destination account as well? So I don't see any problem with creating 2 ledger entries kind of concurrently into somewhere, because it doesn't matter if you get too much money. You'd only need to do that if you had like a limit of how much could sit in the account. Does that make sense? Yeah. Anyone else? Yes, at the back. That is a good question. I actually don't know. Does anyone know? It's for the row level. Yes.
Does Django support nested transactions?
Ah, well, that brings me on to my appendix. It's a really good question, and this is very confusing, and it took me a while to work it out. It's actually really simple. So, yes. So, quick look at how database work in Postgres is Postgres doesn't support nested transactions, but it supports save points. So, within a transaction, you can create a save point at any point within the transaction, and you can roll back and cancel the queries. So, the way that corresponds to Django is if you've got loads of nested atomic blocks, the first one will begin the transaction, and then all the rest will create save points. And then within the context of an atomic block, if an exception is raised but not handled within that particular block, it will roll back to the save point that created. And that will bubble up. So if there's an exception here, then it will roll back to that save point, and then maybe an exception here, it'll roll back to that save point, and then maybe you handle the exception here, so it doesn't roll back the whole transaction, it just rolls back to that save point. So here is an example of that happening. So we've got an inner transaction which raises an exception, which is unhandled, but it's handled outside the atomic block. And what this means is that would be committed, that will be rolled back, and then that will be committed. Does that make sense?
As a follow-up, just wondering about the behavior of the on-commit handler when you're in nested transactions like that. Will the on-commit only happen once the kind of the very top level transaction is committed?
Yeah, I believe so. Good question. Yeah, it is when it's committed, not when it's like because it isn't committed until then, and like you've got to be aware because it's save points. Like once it exits this, it doesn't mean it will be in the database. So although it's atomic, it's not actually a transaction. If that makes sense. Yes.
It's a question which is probably slightly different. So if it's not in the database, if I have a process that's running right now, can I share a variable with another process in Django? I got stuck with this. It's like in Java, you have something like a shared variable. Two processes can share a variable so that if the first process is working, the second process checks. If the second instance of the same process is about to start, it can check if the first one is working or not.
So you're saying you want to be able to have a transaction, but you want to be able to commit. You want to.
Like sharing the variable only. So I found like a hacky way of doing it, like putting a memcache lock. Like I just when the first one starts, I put a variable set it to true in memcache.
Yeah. That doesn't sound like a terrible hack. I mean, I don't know what other people think, but I was thinking some other process like Redis or Memcache or something seems like a good idea. I mean, you can also break out of this completely and like do more lower level commits within Django, or you could even do some raw SQL, but it's a good, does anyone have a better answer than that?
But that's
Depends on it depends what you're running.
that's using Memcache or Redis as a database because it already does
Exactly,
lock. So
Yeah.
it's kind of like doubling.
But it depends on the global interpreter.
Hmm.
Like
I mean, basically, you want to have shared data that isn't, even when you haven't committed it.
Usually the launcher Python will probably have something of that sort.
Yeah. Well, I mean, yeah, I think there's loads of ways of doing it, but probably either something like another data store, or like have a read of the Django docs around database transactions, because you can go lower level, and it might be that you could even start two transactions at once. I don't know, and commit one of them or something like that. Yeah, that's the end. Does anyone have anything else, or shall we? We probably should. Okay, last question.
It's a bit generalized though. What would be your approach to database choice, Postgres, MySQL, and what scenarios will you use?
I would use Postgres always. The reason is, to be honest, I mean, MySQL's good as well, but there's better support, I think, for Postgres in Django. It historically has been better than MySQL. I think MySQL's probably caught up a bit, but also I think it's what most people use who like care about that kind of thing. So I don't know. Shall we have a vote? Who prefers Postgres? Who prefers MySQL? Yeah. Like, just go with the crowd. That's what I do. Cool. Okay, well, thanks, everyone. That's the end of the talk. Feel free to ask me questions afterwards or tell me where I'm wrong. And I'll hand back to Anand.